Good morning or good afternoon. I am Fabien Hugier and I'll be presenting today some recent results from EDEC Infra on airport infrastructures. So from a recent publication by EDEC Infra, it was found that the main driver of ESG data demand from infrastructure investors was actually about managing risk among different other motivations such as reporting for stakeholders and regulators. And infrastructure investors are well aware of the double materiality of their investments and consequently are mainly concerned by the impact that their assets and companies have on climate change, as well as the physical risks that will increase with global warming in near or distant future. So the infrastructure assets and companies are also exposed to the so-called transition risks through their carbon emissions. And the transition risks include policy and regulatory risks, such as the one emerging from carbon taxes, technological risks, market risks, and reputational risks. And it is believed that those 4 different types of risk directly relate to the carbon emissions of those assets. And this is why current regulations are focusing on those carbon emissions, as they make very good quantities that can be easily measured and precisely measured, and thus make good metrics for assessing those kind of risks. So when it comes to carbon emissions, usually we distinguish between 3 kinds of emissions. We speak about Scope 1 emissions, which consist in direct greenhouse gases, including carbon emissions. Scope 2 emissions, which include electricity consumption and others indirect emissions, and Scope 3 emissions, which include a large variety of sources and are actually indirect emissions regarding those companies. So in an upcoming publication by EDEC Infra, we have estimated and predicted the emissions of airport infrastructures globally, with the aim of assessing the transition risk of those assets and leveraging traffic and geospatial data, as will be shown in the rest of this presentation. So a bit about airports. Airports have been increasing in activity since a few decades, and they are now generating about 900 megatons of equivalent CO2 in 2019 before COVID. And this represents about 2.5% of global emissions. So airports, through their activities and through airline companies, are increasingly exposed to transition risks. And well aware of that, airports and groups of airports such as ACI have recently committed to net zero emissions by 2050. As I described earlier, Scope 1 emissions are direct emissions. So when it comes to airports, they are, for example, the emissions from oil and gas combustion for heating buildings, such as the airport terminal buildings. And they are also coming from the vehicles used by the airport. Scope 2 emissions come from electricity purchase, and usually it comes from cooling and ventilation of terminal buildings. And for Scope 3 emissions, there are different types of sources, but we can mention the main ones, which are aircraft cruise emissions, the LTO, standing for landing and takeoff cycle emissions, the use of vehicles at the airports, and the commute of passengers and employees. So at the moment on the ESG data market, several data vendors actually provide data on airports, but when you look at this data in details, you actually find that the number of airports available in this data is actually quite low. And this is mainly due to the fact that only a few airports actually publicly report their emissions. So since this data is so important for infrastructure investors to assess the transition risk, we are proposing a method to respond to these needs. And our method is consists in estimating scope 1, 2, and 3 emissions and other types of intensity metrics using geolocation data, climate data, and traffic data to reach a global coverage of those infrastructures, and use this method potentially for assessing the emissions of other types of infrastructures. So when it comes to scope 1 and 2 emissions, our study has been based on literature review, where some publications have addressed the emissions of terminal buildings. And we collected data of scope 1 and 2 emissions for more than 80 airports, mainly airports taking part in the Airport Carbon Accreditation Program. And we collected different types of data, such as airport characteristics, airport operations, closely located power plants, as well as climate data. And all this data was combined together to create a regression of the scope 1 and 2 emissions against potentially explanatory variables. Here I illustrated some of this data. And the models that we have used combine these different regressors, such as geolocation of assets and temperature, and doing a first regression based on more or less 65 observations for scope 1, scope 2, or scope 1 and 2. We are able to create models which have the following adjusted R-squared shown here in the second line. So we can see that the scope 1 model is actually better than the rest. And when we actually use those 14 regressors, we are actually restricting the data set of airports on which we can predict emissions using this model, since some of this data is missing values. So we have developed a statistical approach in which we generate random subsets of those 14 regressors, compute the adjusted R-squared of those regressions, and use the top decile of those scores to find the best regressors that we can use for each model. So when we do that, we obtain the results at the bottom of the table here. We find that 3 regressors are enough to describe scope 1 emissions, and we find an adjusted R-squared of 0.4. And the same for scope 2 based on 4 regressors, and scope 1 plus 2 based on 2 regressors. And what we find in these models is that scope 1 emissions mainly relate to variations of temperatures at the airport locations and several characteristics of the airports and their terminals. We find that scope 2 emissions depend on the characteristic of airport terminals as well as the number of passengers. And those 2 models results are consistent with the current literature. We found that scope 1 and 2 model, on the other hand, involves different features in the modeling, but it's also complementary to scope 1 and 2. And what we find is that our study includes more data points than usually done in literature. But what is very interesting is that once we have trained our models on reported data, we can use the same regressors on airports not reporting their emissions and predict those emissions using the models that we have found. And for Scope 1 emissions, this gives us about 3,000 airports. Scope 2 gives about 1,700. And for Scope 1 and 2, since we have only 2 regressors, we can predict about 5,000 airports around the globe, as illustrated here. And here we are presenting results about Scope 1 plus 2 emissions. As you can see, some of the data represented here correspond to different data vendors providing data on airport emissions. In red here, we can find the data that has been used to train our model. And I should also mention here that those different data vendors have actually more points which are then represented here, roughly twice more. But we plotted those which were common to our data set. And more interestingly, what we find is that our predictions cover a much higher number of airports. And this is a great advantage for infrastructure investors, as they can reach much more airports for their investment decisions, and they can also compare the emissions of different airports using our data. So for Scope 3 emissions, as I mentioned, we focused on LTO emissions as well as cruise emissions based on the literature as well. The LTO cycle is described in the picture here, and the predictions that we have done were concerning about 8,000 airports. The model that we are using are physical based here because actually most of the airports don't report Scope 3 emissions. When it comes to cruise emissions, only Heathrow Airport actually reports them. And we can reach better accuracy by leveraging the flight information, which is nowadays easy to access. So we have 2 models. The first one for cruise emissions is a distance-based model between airports. And we distinguish between different types of aircrafts. And the LTO cycle emissions is time-based, distinguishing as well between different types of aircrafts. So these are our results, among many others. For example, we see that cruise emissions are much more important than LTO emissions. We have used here color coding independent from the modeling to show different types of airports. The red ones are large airports, the green ones, the small airports. And we find that on average, LTO emissions are about 16% of cruise emissions for large airport and 24% when it comes to small airports. We also find by looking at intensity metrics that Scope 3 emissions coming from LTO and cruise together, divided by the average distance of flights and divided by the number of passengers, actually takes this very interesting shape. We find that, as expected, very large airports have the highest number of passengers, but we see also that those very large airports are the most efficient airport when it comes to emissions in terms of distance and passengers. What we can also see, showing the same quantity against the average distance of flights, is that we can expect 2 different types of populations for small airports, some of them probably focusing on long distance flights and as such having large emissions, and others probably focusing on small distances and thus having small emissions. Finally, if we combine together the predictions for Scope 1, 2, and 3 of airports, which all received a prediction, we get the following distributions. We see in red that Scope 1 emissions are quite close to Scope 2 emissions when it comes to order of magnitudes. We see that Scope 2 emissions have a larger dispersion, but this is expected from the lower quality of the model. And very interestingly, we see that Scope 3 emissions are much larger than Scope 1 and 2 emissions. And this is very important information since Scope 3 emissions are in general not reported by airports and are still very relevant when it comes to estimating transition risks. So in conclusions, what we have found is that airports are under growing exposure to transition risk, and there's not much data available on the market. So to respond to this need, we have developed models for Scope 1 and 2 emissions and Scope 3 emissions, which are able to generate estimates of emissions for more than 1,500 airports up to 8,000 airports. And we have leveraged geospatial data as well as traffic data and climate data to generate those estimates. And the predictions that we got are very interesting for infrastructure investors, as it will allow them to first get an order of magnitude on the exposure of airports to transition risk, as well as compare different airports between each other. And the methods that we have developed for Scope 1 and 2 emissions, which are currently under further developments, could be expanded to other types of infrastructures. And finally, the Scope 3 emission models that we have developed can be applied to different sectors of transport, such as roads and ports and rail. Thank you.